Next up, we're going to talk about another error recovery feature of TCP that makes it a reliable protocol, and this is the duplicate acknowledgement feature. Now, to understand duplicate acknowledgements, you need to understand sequence and acknowledgement numbers and how TCP uses those to make itself a reliable protocol. Now, we talked about this in quite a bit of depth in the TCP section. I'm going to cover it here, but I'm going to cover it very briefly just as a quick refresher. If that's not enough for you, maybe you skipped the TCP section earlier, but you really want to understand this section, you may want to go back and look at that in depth. Now, for our purposes here, the really important thing to remember is this formula, and that's that sequence number in plus bytes of data received equals acknowledgement number out, and that's from the recipient side. So let's go through an example that demonstrates this and demonstrates how sequence and acknowledgement numbers work. In this case, this is the same example from the TCP section where we have a transmitting host and a recipient host. The transmitting host is sending data, and it sends a packet with a sequence number of 5,000 and a data size of 500 bytes. The recipient will take this information and follow this formula. Sequence number in, which is 5,000, plus data bytes received, which is 500, add those together, so 500 plus 5,000 is 5,500, and that equals your acknowledgement number out. So it will send a TCP control packet back to the transmitting host to acknowledge that it received that data, and that acknowledgement number will be 5,500. That's that 5,000 plus 500. The transmitting host sends its second packet, which has a sequence number of 5,500. So it's the next sequence number. So it's the same equation, right? In this case, it's 5,000 plus 500. That's 5,500, and that's the next sequence number of the next packet in line. So the recipient host receives that 5,500 plus 500 data size bytes equals 6,000. It acknowledges with ACK number 6,000. Finally, we have this process happen one more time where the transmitting host sends a packet with the sequence number of 6,000, data size 500. The recipient host adds those together and sends back acknowledgement 6,500. So what we have here is this series of sequence and acknowledgement numbers that take a very prescribed format that account for the amount of data being sent. The cool thing about this is it allows TCP at both sides of the connection to keep a sense of state. And when the recipient host, in one instance, let's say it receives a sequence number but is not acknowledged it, or some number is some amount of bytes is missing, not accounted for in this process, that's when we can have things like duplicate acknowledgement numbers that help TCP detect that an error has happened and try to recover for it. So that's what I want to go into a little bit now with duplicate acknowledgements. So let's go through an example of when duplicate acknowledgements might occur. We'll talk about it in theory, then I'll show you the packets. Now, the important thing to keep in mind here is that the duplicate acknowledgement feature is all about the recipient and the recipient's ability to notice that it's missed a TCP segment, that it's missed a packet somewhere in the communication, and it's an attempt to try to recover from that. So keep in mind the magic here is happening at the recipient, which is a little bit different than what we've looked at previously. Now, in this example, just like the previous one, we have a transmitting host sending data to a recipient host, and we're using TCP. Here we have our first packet, which has sequence number 5,000, data size 500. So the recipient host takes those two values, adds them together, and the acknowledgement number is 5,500. Now, in this case, we would expect the next packet transmitted from the transmitting host to be have a sequence number of 5,500, so the same thing as that ACK number. However, that's not what happens. Remember, in this case, we're talking about what we see from the recipient side. So from the recipient perspective, the next packet we get actually has a sequence number of 6,000 instead of the expected 5,500. And that is weird. That's not the next sequence number we expect. They're called sequence numbers for a reason, right? They're supposed to be, to some sense, in sequence, right? But that's not what's happening. So the recipient host detects this. It detects that I'm missing a segment and sends a duplicate acknowledgement. And duplicate acknowledgement is exactly what it sounds like. It's an exact duplicate of the acknowledgement that it's already sent. So it's the acknowledgement of the with the number 5,500, just like what we see in packet 2, but in this case we're sending it again and sending it to the transmitting host in hopes that it will spur the transmitting host to resend the missing segment. So the transmitting host, when it receives a duplicate acknowledgement, it will take that acknowledgement number and send whatever the next segment should have been, regardless of why it didn't make it to the recipient host. Now, the duplicate acknowledgement, there's not just one of those sent. You can actually send a few of those. In this case, we have up to three duplicate acknowledgements that will be sent for the exact same packet, and hopefully the transmitting host receives one of those at some point. And if it does receive it, it will actually elicit and send a fast retransmission. This is different than a retransmission like we talked about earlier with in this section. This is a fast retransmission, and it's in response to duplicate acknowledgements. And in this case, you'll see the fast retransmission has the missing segment with the sequence number of 5500 and a data size of 500 bytes. So you see that fits the gap nicely between our sequence numbers of 5000 and 6000, wherein all these packets are sending 500 bytes. So the key takeaway here is, again, this is on the recipient host. When it detects it's received or it's missed a segment in the sequence, it will send duplicate acknowledgements, which are exact copies of previous acknowledgements that it's sent, in order to spur the transmitting host into sending a fast retransmission. And this is going to be occurring all the time. This isn't a completely uncommon thing. It would be uncommon if it's happening a lot or if the transmitting host never responds. But regardless of why the missing segment was not received, this is the recipient host detecting that and trying to self-correct, do its own error detection and recovery, which is just another great feature of TCP. I flipped over now to tcp_dupack.pcapng, and this is the file we're going to be looking at to show an in-practice example of what duplicate acknowledgements and fast retransmissions look like here in Wireshark and in practice. Now, before I do that, I've got the first packet selected here, and you'll notice that my sequence number and acknowledgement number are 1, and that's because Wireshark is set by default to use relative sequence and acknowledgement numbers, and that's fine for most of the cases that you'll be investigating. But just for our example here, I want to see the real ones, so I'm going to change that setting by going to Edit, Preferences, go into to Protocols here. We'll browse to the TCP section, and I'll tell it to turn off relative sequence numbers, and that means we'll actually get the real sequence numbers, and you'll see that change applied immediately here, as now we have the real sequence number, the real acknowledgement number, which are a little bit more of a doozy to say, but for our exercise it makes a little more sense just to see the real numbers in this case. Now let's go through the packets here, and we'll start with the first, and we see it's an ACK from 172.31.136.85 going to 195.81.202.68. So in this case, this 172 address is our recipient, and 195 address is our source. We know that because it's the direction the ACK is going. And you might ask, well, what is this acknowledging? We don't see a data packet being transmitted, and that's correct. The data packet that this acknowledgement is related to is not included in this capture because to some degree it's quite honestly irrelevant. We're going to start our analysis here looking at the acknowledgement number that's present here. So we see we have an incoming sequence number and we have an acknowledgement number, and the acknowledgement number here that we're sending back is what we're really concerned about. We're not concerned about the sequence numbers going the other way. We're concerned about this acknowledgement number, and that number tells us what we should expect next, what segment we should expect next, and it looks like it should be 131.09.73.186. You can also see that maybe a little bit more clearly up here in the packet list window. We see the acknowledgement number, in this case, going out. So let's look now at the second packet and see if it's the sequence number we expect. And the best way to do this really is staying within the packet list window, and you can look very clearly here that it is not what we expect. We expected this to end in 3186. It ends in 4130. So this is not the segment that we expected to receive from the recipient's perspective. We expected to see something with this acknowledgement number here, but we don't get that at all from 195.81.202.68. So that means that a segment in this case has been lost, at least from the recipient perspective. At least it didn't receive it. So that may mean that the sender didn't transmit it. It may mean that it was lost on the wire. We don't really know, but it does mean the recipient didn't receive it, and it's detected that. So now it's up to it to do something about it, which it's going to do through the duplicate acknowledgement process. In this case, since the recipient was the one that detected the issue, it's responsible for fixing it, and it sends its first duplicate acknowledgement here in packet 3. And there are a couple of ways you can tell it's a duplicate acknowledgement. First of all, it's formatted with the color of having a black background and a red foreground, so it's that error state that we see with a lot of other types of TCP type errors. It also says here in the info column that we have a TCP duplicate ACK1 number 1. So it's the first duplicate ACK that we see here. And of course, you can also look at the acknowledgement number. So we see the acknowledgement number here is 131.097.3186, which is the same thing we saw up here in the first packet, looking right here in the info column as well. So that's how we know it's a duplicate acknowledgement number. You can also see that down here in the packet details window. If you go down to the seek ACK analysis section, it'll tell us here that it's duplicate to the ACK in frame 1, and then its severity level is just a note. It's not an error or a warning because this sort of thing does happen. It's perfectly normal to see duplicate acknowledgements on the wire. It's only when you have an excess of them or you have an unrecoverable communication sequence that it's really incredibly notable. So in this case, it tells us what the acknowledgement number is. So that means we know what the next sequence number we expect is, and it's this one ending 3186. So the next packet that comes back still has the incorrect sequence number. It looks like it was maybe transmitted maybe before the duplicate acknowledgement was received and processed. And this actually happens a couple more times. So we see another duplicate acknowledgement here. You see it's duplicate ACK number 2. We have another out of order packet, not the one we necessarily expected to see. And then finally, we have a third duplicate acknowledgement here. So these packets 3, 5, and 7 are all essentially the same as packet 1 here, which is our acknowledgement. Wireshark has just detected that it's a duplicate in this case. So there's nothing particularly in the packet that signifies that it's a duplicate ACK. There's no flag set or anything like that. It's actually Wireshark doing this analysis as the source in this case, or as the recipient of the duplicate ACK would do the same analysis here. So it's Wireshark providing that value to us. If you were looking at this in something like TCP dump, you would actually have to spot that the acknowledgement numbers were the same. I don't believe it will tell you this right out of the box. So that's what we have with the duplicate acknowledgements. Fortunately for us, the communication is recovered, and we see that happen here in packet number 8, where we see that this is denoted as a TCP fast retransmission. And notice that the sequence number of this, 131.097.3186, matches the acknowledgement number in all of these duplicate ACKs. So this is the segment that was missing, and the host at 195.81.202.68 has now sent that via a fast retransmission, which means it stopped what it was doing and sent that out, and then resumed sending its the rest of its communication. It sent that out, and we've received that, and that data can then be acknowledged appropriately. So this is an example of duplicate acknowledgements being used to recover from what is essentially an error state. This is another reason why TCP is a reliable protocol, is that even when a segment is dropped, one of the endpoints can detect it. In this case, the recipient detected that a segment was dropped or lost somewhere and initiated the process to recover that segment. And fortunately for us, it worked, and that segment was received and communication was good to go. To summarize what we've talked about here, keep in mind that duplicate ACKs occur when the server detects a packet coming from the client was lost. So we're missing a TCP segment in this case. And we're using the term client server. Earlier we used transmitter and recipient. In this case, we're saying that the client is sending data to the server, and whoever the recipient is, in this case the server, detects that packet loss has occurred. Now, one other thing I want to talk about here is selective acknowledgement, just very briefly. And we talked about selective acknowledgement, or SAC, when we talked about TCP. And it's an option for TCP which allows for the selective acknowledgement of segments. And it's important when we talk about duplicate ACKs, because in our example, you'll notice we were only missing a single segment, and the client in this case retransmitted only that missing segment, and that was the only thing it had to do. And that's because selective acknowledgement was enabled for that particular communication, as it will be for most of the analysis you do. However, if you encounter something where selective acknowledgement is not available between two TCP hosts, what would happen is that not only would the missing segment be retransmitted via fast retransmission, but all of the segments after that would be as well. We didn't see that in the capture we looked at. We saw other segments that were there and received after the duplicate ACK was sent, but were not retransmitted. If selective ACK wasn't enabled, you would see all of those retransmitted. So I want you to be prepared for that, just in case you happen to run into it. Finally, if you suspect that a server isn't receiving data, you may want to capture packets from the client side. Remember, we're dealing with a scenario in which packets are being lost somewhere. And so not only do you have to validate that a packet isn't being received, but you may also need to validate whether or not it's being sent in the first place and where the loss is occurring. So you may have to capture packets at both the server and the client, or maybe even at a couple steps along the way if you're going across a few different router hops or something like that. We're dealing with a packet that's been lost and the recipient has detected it's been lost. So either it's not being sent or something along the path to the recipient is not allowing it to get there, and we have to diagnose that by using some of the techniques we've talked about here. Now, in a lot of cases, you won't have to move around too much. You should be able to see the duplicate acknowledgements, because a lot of the time you'll have the first packet is received and the third packet is received, but the second one isn't. So again, often a very transient, temporary state. You only have to really worry about these when you have a lot of them occurring at once, or when the connection is ultimately terminated because segments were lost and not recoverable, which usually means maybe something, the source of the communication has gone down, or something in between has as well. But I tend to think of duplicate acts kind of as the functional opposite of a retransmission, because it's the recipient detecting the error versus the sender. But kind of two sides of the same coin using very different mechanisms. But you'll want to be familiar with retransmissions and duplicate acts in practice if you want to be better at diagnosing latency on the network.